So, yeah, so sorry, I'm gonna be a little bit all over the place. Well, do you want me, I can stick to this Blackboard. So, okay, so to start off, just wanna talk about, so big picture on sort of like mathematical modeling, right? So, there's sort of two sort of general approaches. So you think about like a theory-driven approach and then like a data-driven approach. And so over here we have like our prototypical example will be like general relativity from physics, where it's a largely theoretically conceived model. It depends on very few parameters, but it took a bunch of like upfront thought and creativity to come up with. And then over here, our sort of prototypical example for like on this end of the spectrum will be like machine learning. Here we have models that depend on, like hundreds of thousands of parameters, right? They're very general, but they have high computational costs, and sometimes when you get the results, they can be harder to interpret. So what we're going to be talking about is sort of somewhere in the middle here. So this is my thesis, and this broadly falls under the category of data assimilation. Where we have some physically motivated model, but our goal is to figure out how to incorporate data into that model. So data assimilation is the scientific discipline that seeks to optimally combine theory with data for dynamical systems. And so, yeah. So in particular, I'll briefly outline the nudging approach to data assimilation, and then we'll move on to my thesis, because my thesis all takes place within that framework. So, okay. That's the big picture. Okay, so we were talking about nudging, and this approach comes from a paper by Iwani, Olson, and Titi from 20. Okay. So we start with some dynamical system, dot plus f of u equals 0, and u of t equals 0. So u dot represents time differentiation, and there's some initial conditions. So the systems we're interested in will be generally be dissipative, chaotic dynamical systems. So because they're chaotic, they have sensitive dependence on initial conditions, and so we, so in particular, because you can never know this, the initial conditions completely, your errors in the initial conditions will be sort of amplified over time. So let's assume we have some simulated system here. So this is some V is some simulation of our, this is like the ground truth here. This is like our model here. So U will be like our true system or our reference system, and then V will be our simulated, like our model system. In particular, since we don't know the initial conditions, so the errors sort of in this initial condition, the error in this system will grow over time. But now we assume that we can observe this, we can observe our true system, and so if we could observe it exactly, we could add some term here that was just the difference, and this would push you from your like incorrect model system, and it would take your observations and push you towards the true system, right? But obviously, we have the same problem as we had with the initial conditions here, because we can't observe the complete state of the reference system, and so instead what we do is we nudge with they called it general interpolant observable. We nudge with some observation of which represents our sort of partial information about the true system.
Sorry, Josh, is that just multiplication, those those braces?
Yes, yes. This is multiplication. Mu is just some real parameter. It's some, and so this is, and so sort of the remarkable thing about this is that, you might expect that this would just lead to convergence of, I'm assuming we're in some, like that this is in some Hilbert space, so we have,
like a metric? Yeah, okay.
Yeah.
You have a norm, okay.
Yeah. This is some, we'll get in some like real Hilbert space. And in the original paper, they did everything sort of more rigorously. I'm just sort of giving the bare bones. But this doesn't lead, it doesn't just lead to convergence of the like observed error here, right? It also leads for sort of the proper choice of our interpolant observable. So these interpolant observables, they represent like an observation at large scale or some like coarse graining of the system. And they, in the original paper, they described sort of, they looked at particular choices of that, and they gave like conditions on things that this for this to converge. But for a good choice of this, it doesn't just lead to convergence of this observed error, it also leads to convergence of the entire error. And so part of their, part of what's going on a little bit in their like initial motivation is because these systems are dissipative, they have, a lot of times they have, even though they're, generally a lot of these will be like infinite dimensional systems, they have like finite dimensional attractors, and so that way here you're sort of getting at sort of all the information you need about the system to nudge it. Okay, so for simplicity, for the rest of my thesis, so that's sort of continuous state assimilation nudging. So for the rest of my thesis, I'm going to assume that our Turbulent observable is a projection operator onto some finite dimensional subspace of our state space. So I'll assume it's some projection operator that satisfies everything you want a projection operator to satisfy, so it's like
You square it.
self-adjoint and
You square it.
and-
You square it. It's the same as doing
Yeah.
it once, right?
Yeah, and particularly it's linear, we're gonna use that a lot, and, yeah. And we'll assume that it like we'll mostly assume that it commutes with, like spatial differentiation. So, like usually in like when we get to the, so we'll do this we'll sort of go through a couple examples at the end, and, for like the infinite dimensional example, we're gonna just look at, this will be like Fourier projection. So like the truncation onto the first n Fourier nodes. Okay, so, yeah. So this was originally studied in this paper, and then it was extended in several other papers, which I referenced in my thesis. But now, what we want to consider is we want to consider what happens when we modify this. So instead of the form of the dynamics being exactly known, we assume that it's only known up to some finite number of unknown parameters. So instead of what we have before, now we have so P here is just because now that's just our interpolant observable. But the important difference is that here now we assume that this is some function of our like state, and then some parameters in our n. And we assume that the form of the function is known, but that the parameters are unknown. So gamma here will be some vector of unknown parameters, like our sort of true parameters, and then C will be our approximate parameters. Okay.
So Josh, I hate to do this, but
Yeah.
just to make it concrete, if I'm looking forward to something like the Lorentz model that you look at later, these gammas would be like maybe the true state of the atmosphere, things like the pressure and density. And just
So it'd be like the true, so gamma would be like the true, like, so the parameters in the Lorentz, but like the Rayleigh Prandtl number.
Yeah.
So, or like, I don't think I go through Navier-Stokes, but like, it could be like, this could be like the viscosity or something like that. That's what would be like a fluid dynamic.
These are physical qualities of the system that we kind of
Yeah.
know but don't know exactly.
Yeah, so they're like, yeah, they're kind of like the physical constants of the system.
Okay, constant. So they can't themselves be dynamical.
Yeah, no, here we're assuming they're not.
Okay.
dynamical, yeah.
Okay.
Not yet.
Not yet, yeah. That's maybe the next step. Okay. Yeah, great. So now our goal will be to minimize, or I'll call it I of UV, which equals 1/2 our projected squared error. So find the ideal choice of C that minimizes this error. And so, and because nudging works, this should also sort of minimize our total error, not just our projected error, hopefully. So obviously, in this case, the solution would just be C equals gamma. But here gamma is considered unknown, so we want to figure out ways to find it, just given sort of observations of U. Okay, and then later on, so this is sort of the setup that we'll be considering for most of this. At the end, I'm briefly going to look at sort of if we look at the modification. Where here f tilde is some like approximation of our dynamics. So because this is sort of, in the real world, this is sort of actually what's going on. I mean, sometimes it's a good enough model that it doesn't matter, but for example, like with fluid dynamics, you don't actually simulate the individual velocities of the molecules. So that would be sort of what this represents, and then you simulate some mean, some statistical approximation of that, right? Okay. And so you sort of, eventually we want to sort of look at this, and this is going to be, but we don't, yeah. So, great. Okay, any questions? Okay, cool. So now we'll talk about our assumptions. So we have sort of three big assumptions. These are sort of originally motivated by like numerical experimentation, and they've sort of been, in specific cases, they've sort of been more rigorously analyzed, and it may be possible to sort of formulate weaker assumptions, but these are sort of the sort of idealized nice case assumptions, and in particular, so what we're going to do is we're going to develop sort of a framework for estimating these parameters, and this problem has been sort of studied a little bit already, but we'll show sort of that, for example, we find that like we're able to understand using this framework we talk about that one of sort of the cases that was already studied is a specific realization of the ideas we're talking about. Okay, and then also most of what I've done is not completely mathematically rigorous yet. It's largely we're sort of working very generally, and so we're gonna there's still some more steps to take in terms of rigor, but we sort of will rely at the end on numerical experimentation as sort of the evidence to back up what we're talking about. Okay. Great. So the first assumption will be that for large time, so this is assumption one, for large time the error is approximately constant. So this is for some, this is that t, for some t considered large. And so, yeah, so we see this plot here, we see that this is for different values of the parameter error. This is in the Lorentz 63 system, which we'll consider later. We see sort of that what happens with the nudging. The nudging converges up to a point, and then the error remains sort of approximately constant at a constant level over time. And so, what does this mean? This means that we have that this is approximated by some function of our parameter and possibly our initial conditions. Okay, so that's assumption one. Okay. Assumption two is we're going to say, we're going to assume that this long-term error function is independent of our initial conditions. So that means that we have then in particular, the long-term error is just some finite dimensional, some function of just Rn, right? And we can see that here, right? So this is where there's some parameter error, and what happens is like this is for like randomly sampled initial conditions for the Lorentz system. The nudging converges, and eventually for all these different initial conditions, the sort of long-term behavior is the same. Yeah?
So how much of a assumption is this? I mean, my very naive understanding of dynamical systems is they have this extreme sensitivity to initial conditions. So this is not the system itself, it's the error, but somehow.
Yeah, so I mean, there's still sort of sensitivity to initial conditions in U, but we're sort of, for our like model system V, right, it looks like this, right? So we're assuming that the nudging has basically overcome sort of all of the dependence on the initial conditions of V. So there can still be sort of dependence on maybe the initial conditions of U, because the important thing is we're sort of, what we're going to do is we're going to sort of form this as like an iterative algorithm for updating the parameters sort of as regular intervals. In order to do that, we're going to have to change the parameters and then sort of restart our model system. But U is just sort of running this whole time. So there still might be dependence on sort of the initial conditions of U, but we're assuming that like the nudging sort of washes out sort of the dependence on the initial conditions of V.
And none of this depends on the existence of an attractor, like a lower dimensional attractor? That's irrelevant, probably?
Well, I think it's related, so we're still in like we're still considering like a dissipative dynamical system, right? And so that's part of what makes what makes this projection work is because so I mean, sort of the theory behind nudging sort of is related to the existence of a attractor, and so we're assuming that we're in sort of some framework where nudging works, right? So so I think we might have to assume that there's like some finite dimensional attractor and stuff like that. But yeah, does that answer your question?
Yeah. And then remind me what dissipative means, because if I think about the Lorentz equations, most things I think about dissipative means sort of everything goes to zero, but dissipative here is the more general idea of what?
I think like there's some So I have to remember, and Jared, correct me if I'm wrong, but there's like some absorbing ball so that like, no matter how
Oh,
far away from zero you start, like, you
Oh,
have to be
like
careful
the-
with the order of the quantifiers,
like
right,
the,
but,
like the Lorenz equations.
eventually you
How's
sort
that?
of end up
Yeah,
in sort of some,
yeah, and that's pretty easy to prove. The Lorenz
Set.
equations have that.
Yeah.
Flow is not divergenceless.
Yeah.
It's in a compact set, so.
Yeah,
yeah, it's like bounded.
it enters this
Yeah,
place of no return, no escape, I guess. Right? So-
yeah. Yeah. Okay. Yeah. So that's assumption 2. And this is sort of important because, yeah, as I sort of said, we're gonna sort of be, this is sort of gonna be like an update thing where we regularly stop the simulation, update the parameters, and then restart the simulation for V. And so, yeah. That's why that assumption is important. Okay, so the third assumption is we're just gonna, because what we're gonna do then is we're gonna do, apply sort of we're gonna apply nonlinear optimization methods on, like finite dimensional nonlinear optimization methods on E. And so in order for that to work, we need to have sort of at least local convexity, and differentiability, because it'll be like derivative-based methods of E. Yeah. Okay. Also, just a few words on this error function, right? Because we're assuming nudging works. That means that we have E of gamma equals 0. So when we plug in the correct parameters, the long-term error converges to 0. And we also have, just by the form of our error, that it's greater than 0 for all choice of parameters, right? And then, yeah, so this means that E has a root that also must be a minimum at our correct choice of parameters. So that means like the multiplicity of the root is at least 2.
So you want to talk about multiplicity? Because you use the bigger name convexity, which you don't necessarily have to have differentiability to have convexity. So convexity
Yeah.
seems like a weaker, sort of kind of a cooler thing, right?
Yeah, yeah.
So
So this is I'm just sort of sorry, these just immediately, so I should sort of separate these from this assumption. So these sort of immediately just follow from the
just the
from the
word,
definition
just the
of-
word you
of
said
our-
about. Seems like you said something about a second derivative or something, but maybe not.
Yeah, well, so importantly, right, so we're gonna implement sort of optimization methods on E, but we're also can implement root finding methods on this error. But importantly, because the root is like because it's a root that's also a minimum, it has a multiplicity of at least 2, right?
If it has a multiples, I guess. Okay.
Yeah.
That's
Well, if it's, assuming.
if it makes sense to multiplicity makes sense, which convexity doesn't necessarily, I don't think, mean that, but yeah. Okay.
Well, we're assuming it's like differentiable and,
Okay, there you
assuming you can like
Mhm.
locally expand it as like
So okay.
as a series or something, right? Yeah. Okay. So let's press forward. Okay. So here on the
Yeah, there's-
board, you can see that's sort of
Mhm.
plotting this
Oh, so-
in particular, right? So this is sort of
Oh,
plotting
differentiability.
around this here. 10 is the correct value of the parameter,
Okay,
right?
duh.
And then this is looking at the sort of long-term error. So this is sort of, we've allowed the system to relax here, right? And then this is looking at sort of the error at different parameter values. So we see it has this sort of convex structure.
I just missed the DIFF there, so
Oh, you missed the
yeah, that's
differentiable
why I
part.
was
Okay,
fixated on something irrelevant, but
okay, yeah, that's gonna be very important because we're gonna be taking derivatives, so. Okay. Great, so, okay. So if we make these assumptions, now we consider what the derivatives of our error look like. So partial E partial Ci, so this is with respect to the ith parameter, is going to be half partial Ci P V minus U. So here, this is where I'm going to use the fact that we're using some like
inner product.
norm on our, yeah, some inner product on our Hilbert space. But in particular, it's sort of easy to see how to generalize this to like different norms and things like that. And that's sort of one advantage of this method too, is that we can see how to generalize it to different, minimizing sort of different norms as long as they're sort of well posed, like differentiable. So this will be this if where W sub I is, because I'm going to be using this a lot, is the derivative of our model with respect to our parameter. Okay, and this comes like when you think about there's like a product rule going on here, and then the inner product is symmetric, and so you can combine those two. Okay.
That'd be harder for or just any norm.
Yeah.
Or yeah.
Yeah, it would be, yeah. Okay, and then some points we'll think about the second derivative, which is going to be, and I'm assuming that our projection operator like doesn't depend on our parameters, so it commutes with all this differentiation. This is at our large time. Right, okay. I guess I don't need the P on both sides because it's
Sure.
Bottom information. So, okay. So now this means that, so we sort of, so this is W sub I is this, and then I also call Z sub ij, this is Z sub ij I have here, is partial Ci, partial Cj of our model system. Okay, great. Yeah, so now the question is how do we estimate W sub I and Z sub ij? These are called, so like these WIs are called like sensitivities a lot of times because they represent like how sensitive your system is with respect to parameters. And if we take the derivative of our model system, our nudge system with respect to the parameter, then we get the following dynamics for W sub I And then because our initial conditions don't depend on, if we assume the initial conditions don't depend on the parameter, which is sort of the natural case, right? Then we just have 0 initial conditions. And I don't know if I mentioned this earlier, but usually, so mu here is our nudging parameter. And usually it's best to choose this large, sort of as large as you can, while still sort of maintaining numerical stability. And so, in particular, we see that mu has like a dampening effect, like a decay effect on our sensitivities. And
If it's positive, I guess?
yeah, mu is positive.
Oh, okay.
Yeah, otherwise you'll nudge yourself
Okay.
away from the correct system.
Well, this is the
Like-
first time I noticed that
No, yeah,
that
yeah.
matters, so.
Yeah, yeah. And then, yeah. And so this will allow us to do perturbation theory in mu being large, and then because things are also simplified a lot because we have 0 initial conditions. So these are called like the sensitivity equations. Here, this df is the differential of f in v, so like the Jacobian in v, and this is the derivative with respect to a parameter with v constant. Okay. Also, I'll briefly write it out. We have the second order sensitivity equations. Do this again. And here I'm sort of, I'm using like the finite dimensional notation because if we have infinite dimensions, we have to be careful about like, you know, how we define this as some like Fauché derivative or variational derivative. But it's pretty clear to see what the sensitivity equations look like even in the infinite dimensional cases. We'll see because you can see how to take the derivative of the system. And then these also have 0 initial conditions.
Sorry, this is too interesting. So the part where you have the df, you know, of v, comma, c vector, wi, that, I can imagine writing that out pretty explicitly. What does it mean when it's df of a, shall we say, a 2 tensor?
You mean this? Oh, so this
So
is
on
d-
the first part there, the d squared I don't really, but doesn't matter.
Yeah, so df of so in particular this is df in the v space,
Yeah.
right? So
Oh, this,
I and j are free indices here.
but is the df there the same as the df above? But you've got this
Yeah.
argument
yeah. So this
that's
is,
sort of a matrix now instead of a vector. When it's a vector, I totally get it. I can't.
well, it's like in particular.
Oh, so it's just kind of. Oh, so
like,
it's sort of a matrix times a matrix, or something, which is a
so
matrix.
this is just the chain rule here, right?
Yeah,
but,
yeah.
But
But it's like a
if-
directional derivative and stuff, and I just don't know what it means when it eats a.
So let's say here's what I'm saying. So say H is Rm. df would be and then our parameter space is Rn. So this would
Yeah, I know.
be,
So I and j are fixed and stuff, but
so this is so I is
so
fixed
I
here,
like to
right?
think
So
of df
this,
as like a matrix,
so
and
yeah,
it's
this is an m by n matrix.
right, and it multiplies the vector, and I know
And
what
this
that.
is so V is an m-dimensional vector, right? And so this would be like
And so
m by n
so below
matrix.
when df is acting on a 2
this
times.
is still an m by n matrix.
So it's
Yeah.
just sort of a matrix times a matrix. Then?
Well, no, so it's a matrix times a vector. So we have to be careful about indices, right? So W if I was to expand in the basis of, like a basis for our Hilbert space, which say is Rm, right, let's
Mhm.
do finite dimensions, then W, for each I, W is an m-dimensional vector. So you could think of W as a matrix, if you want, and this is like so Z is sort of like a, yeah.
So it's like W is like a vector in the space that V lives in, but you can also think of it as a matrix with one index in the V space and one index in the parameter space. And then Z is also a vector in the V space, but a matrix in the parameter space.
Yeah.
So it has three indices, but only one of them is the kind that can, only one of them is the kind that lives in the V space. And that's the one that DF is attaching to.
So if we were to use just tensor notation, I would maybe understand it better or something. I don't know.
Yeah, you just
Yeah.
have to use different types of indices.
Yeah.
Alpha
Some Greek,
for
some
Y.
Yeah, if I use, so, but in particular, right, we're sort of thinking about, yeah, so we're sort of thinking about, we want to go to like infinite dimensions at some point, and then, you know, I mean, I guess you could expand as a Fourier series or something, right, but you have an infinite number of indices, right? But yeah, so, yeah, does that make sense?
Maybe.
Okay. Well, let's keep going, and then, yeah. Okay, it's like we have a vector for each index I, and there's a vector. If I use like vector notation.
So he said component wise. So when you get done doing that DF, you know, eating, shall we say, WI vector, does it spit out
There's
something?
still going to be an I index.
It's still gonna be I index left.
Yeah, and this
So
is still gonna have an IJ
the thing that I
index
want to
left.
think of as a matrix is not sort of contracting with that index.
Yes,
It's
right,
not
that's right.
contracting with that index.
Yep.
Okay.
That's right. Okay, so now, the next step is we want to consider just this equation for W sub I, and then we want to do perturbation theory in mu going to infinity. And just look at sort of what the leading order behavior looks like. And to sort of put rigorous sort of asymptotic bounds, you have to know a lot about sort of the behavior of V, and so we're just gonna press forward and assume that we can do perturbation theory and see what we get, and then rely on sort of numerical evidence. And later, you know, it will reserve for future work, doing the more sort of rigorous justification. Okay, so, so here we want to consider mu being very large, and then, so in particular, if you take mu to infinity, the system sort of becomes non-dynamical, so what we want to do is rescale our time variable so that we get back some dynamics. So then we do tau equals mu t, and then we write W sub I of t equals cap W sub I of tau, and then we have W dot sub I equals partial tau partial t of cap W sub I of tau, which equals mu cap W sub I. Dot, where here dot just means differentiate with respect to
So
the
there's,
argument.
okay, so there's a dot over the WI, just a little bit left to that.
Yeah, no, partial tau. Yeah.
Okay, all right.
Okay. So then, this gives us, then if we take the equation I just erased, which I probably should have waited to erase, and then we divide by mu, and then we let epsilon be 1 over mu, we find this. We find this equation. And then now we can do perturbation theory in this, and get something dynamical out.
Okay, so this is that business of making your, mu as big as possible, right? And then-
Yeah. This is, so here epsilon.
So the main dynamics
one
are
over mu.
definitely just goes to zero, right?
Yes, right. So the order one approximation, is W. Okay, so we assume that W's y can be written as some perturbative series in epsilon.
And there's no need to do multiple scales on the time itself, right?
Yeah.
Okay.
No, yeah. Okay, so the sort of order one approximation ends up being, as Scott points out, so the order one approximation is just for to decay. It's just zero, right? So because we start out, so this is at t equals 0, and so that leads to, so this sort of leads to a decaying solution, but a decaying solution with zero initial conditions is just 0. So we get sort of identically 0. But then if we move on to the next order, so we go to sort of our first order approximation, then we get, and we really want to estimate our projected sensitivity, because that's what enters into the derivative. So we get something that depends on W0, but that's 0. Okay, so we get this also with 0 initial conditions. And you can use an integrating factor on this, and you get the solution.
Was there a derivative?
How?
Was there a derivative on the line just above that?
Yes, sorry, this should be,
Okay,
yeah, that has a time derivative. Yeah, so this is sort of our approximation, but then we can simplify this. If we put things back in terms of t, then this leads to an approximation for little w's y of t, which, here, I'll erase this now. So I've done a change of variables and a couple other things, but if you do that, you get this. And then if you use Watson's lemma. This is like an exponential integral. If you use Watson's lemma and consider mu as our large parameter, so this is exactly the form of Watson's lemma, which looks at integrals that look like the form of this. And it says, so this is Watson's lemma. And yeah, when we do, if we're doing like, especially the infinite dimensional case of this, we have to be careful when using this, or we have to do more to rigorously justify using this, but it leads to this asymptotic series, and then, so this is for lambda going to infinity. So if we apply that here, and we look at just the first order approximation,
This seems like just, the usual statement about Laplace transforms or something.
That's how you justify,
Those statements.
yeah.
This is kind of the right way to think about it.
You can justify Laplace transform using Watson.
Okay.
So
Yeah.
notice that T doesn't show up on the right-hand side of that.
yeah, here it shows up because it's going to stay around because it's in this argument here. But
Watson's lemma basically eliminates the dependence on the bounds of the integral.
yeah, but yes, it eliminates dependence on the bounds of the integral. Yeah, but it still shows up in here when we look at this. So this leads us to the approximation to leading order. Yeah. And for z sub ij, you get something similar. But if in particular you have like linear dependence on your parameters, and then sort of now the leading order is second order and 1 over mu. Here, and this, I'm using the sort of tensor notation that this, with these parentheses, represents symmetrizing over the I and j, making this symmetrical. So, okay. Yeah, sorry, okay. Okay, so, very briefly, we're following sort of the relax then punch paradigm for parameter estimation, which involves, what do? We let our system relax until the error is constant. Then here you do a parameter update and you let your system relax. And then we and then you restart your model and then let it relax again, and then you do the parameter here once it's relaxed, you do the parameter update here once it's relaxed again. And so this means that we need to choose our parameter update times at intervals that are spaced some delta t apart, which is large compared to our relaxation time, but since mu is large, our relaxation time is sort of order 1 over mu, so in practice delta t doesn't actually need to be that large. Okay. So in particular, if we we consider single parameter estimation, we can apply Newton's method, which says, and we do it for multi-parameters, but I want to look at the single parameter case real quick. And then it's a root of order 2, we can multiply by 2 here, and then if we do that, we get the following parameter estimation algorithm. Okay, right, this is our sensitivity with respect to the parameter. So the really cool thing is that if we consider, if Carlson, Hudson, and Larios in a paper in 2020 considered doing parameter estimation for systems, for a system that looked like a form, looked like this form that I'm about to write up here, is the 2 Navier-Stokes equations. L U plus U equals 0, E dot plus minus C of E plus F E plus mu E V minus U equals 0. They considered this, and if you use our do our perturbation theory on that, then you get C of K plus P, Newton's method, Newton's root finding method, leads to this, which is the same algorithm that they looked at when they did parameter estimation on this, using sort of a different derivation. So this shows sort of that this sort of like can provide a framework for understanding some of these algorithms, and can show how that algorithm fits into a larger framework, and in particular, we can also, so this is sort of applying Newton's method. You can also apply, in particular, Newton's root finding method. You can apply sort of, and I outline sort of the details of this, because press for time, I won't go through it now, but outline the details of this in my thesis, but you can apply Newton's optimization method, or sort of approximations of that, like the Gauss-Newton method, or the Levenberg-Marquardt method, which is like a regularized version of the Gauss-Newton method, or sort of like that. And you can get sort of other algorithms for sort of estimating parameters. And so now we'll sort of look at how those compare numerically. So we'll sort of go through, we're really short on time, so we'll quickly go through sort of the 3 applications. So first we consider the Lorentz 63 system. So this is a model for like convection in the atmosphere. It's a very simplified model. It's only 3-dimensional, but it still leads to sort of interesting chaos. It's one of sort of the simplest examples of chaos. So using sort of the notation I've been using over here, this is what we have. And here I'm nudging using the entire state rather than some projection of the state, mostly because I wanted to look at sort of fitting all 3 parameters. And there's some sort of dimensionality issues if your the dimension of your projector is less than the dimension of the number of parameters you have. So here in particular, we implement this is sort of multi-parameter estimation with gradient descent, This is Newton's method and Levenberg-Marquardt. Particularly, this is sort of so what I wrote on the board was the single parameter version, the single variable version of Newton's method. This is sort of one way of generalizing where you use the gradient to tell you which direction to go down. There are sort of other ways if you can break up your function into like a sum of other positive functions. And so, yeah, so this is, so we see sort of, in particular, like, all of the algorithms converge, but very different convergence rates between them. Here, this is comparing, so I called, this is in the thesis, but I didn't say it here, so what we can do is we can use the perturbation theory for the sensitivity equations, or we can directly numerically simulate the sensitivity equations. So DS here comes from actually simulating numerically the sensitivity equations, and then OTF stands for on the fly, that stands for using the perturbation theory, and using our approximations of the sensitivities. And we see sort of very similar behavior either through direct simulation or using our asymptotic approximation. And here this is sort of justifying the, so in these other cases, in particular our nudging parameter is chosen very large, it's 100. But this is, you know, sort of looking at what happens is sort of you increase your nudging parameter and you see sort of greater and greater agreement between the direct simulation methods and the on-the-fly methods, sort of providing sort of numerical justification for the perturbation approximation made earlier. So that's the Lorentz 63 system. We also applied this in the Lorentz 96 system. So this is a model for like wind movement along a single circle of latitude. In particular, this sort of is a nice model because it's a ODE model that allows you to look at sort of two different scales. I called, you know, U super L, I called, this sort of isn't the standard notation, but I'm trying to make it match the notation I used everywhere else. So I called U super L like the large scale, right? And then U super S is like the small scale. And so each large scale interacts with, in our case, there's 5 small scale variables and has this sort of nonlinear interaction with them. And this is our nudge system, and in particular, we're nudging only on the large scale. And here, something weird happens. So I think this is sort of the we can see what sort of happens when you see the failure of some of our assumptions. Because there's this weird sensitivity to the parameter update interval, which I didn't show it, but there wasn't really that sensitivity in in the previous system we looked at or the next system. And I think this is because the times when it doesn't converge, that you hear pure, it actually converges to the negative of one of the parameters in there, and that was the parameter on the nonlinear term. So somehow the nonlinearity may be factored into that. But this is sort of a failure of our assumption of convexity of our error function, and that means sort of, it also seems like then sort of different ways that your algorithm sort of starts out, like depending on your time step or your nudging parameter, it will just sort of push it to a region where it will converge to the other one. And then now we turn to a PDE case. So we look at the Kuramoto-Zibashinsky equation. So this is a model for turbulent behavior in plasmas, as well as a few other sort of physical systems that it corresponds to. Looks like this. We take our projection here. So this is simulated on 1024 spatial array. We take our projection, wrong way. We take our projection operator to the projection under the lowest 32 modes. So in particular, you don't need that much. It's like throwing away sort of a ton of the higher mode information, and so the nudging doesn't need that many modes to converge. And we find the sensitivity equation. So first I looked at sort of estimating only C1 here, because there's some interest, because then you can sort of, there's only one extra sensitivity equation for both first and second order. And so here we can do a comparison between, here this is, so the top is Newton's method, the bottom is, so it's Newton's method again, but it's Newton's method when you apply it to the gradient. So it depends on the Hessian, so I just called it the Hessian method so that it didn't get confused with Newton's method. And then Levenberg-Marquardt is like an approximation of that lower one where you ignore one of the terms that's small. And as you can see, we sort of see similar convergence rates between these two problems, these two approaches. So in red we have sort of the state error, and then green is the parameter error. And then here we look at sort of, so this was directly simulating the sensitivity equations. And then here we look at sort of using our on-the-fly methods and comparing those with the direct simulation. And interestingly, for like Levenberg-Marquardt, the on-the-fly method converges actually faster than the direct simulation method, and that happens in a couple different places in my sort of experimentation. And it may be that sort of taking this perturbative approximation, because sort of by picking mu large, that mu is sort of our relaxation parameter, so by picking mu large, you may be sort of getting at sort of the essential aspect of the long-term behavior. I'm not exactly sure, but yeah. And here we can look at comparing so this is the CHL algorithm, so that's the one from the 2020 paper by Carlson, Hudson, and Lars. And we see that this is the Newton's method, and this here is the Gauss-Newton method. So this is where you do the Hessian method, but you ignore sort of one of the terms in the Hessian that you say is small. We see that they have sort of very similar forms. Here, right? Yeah, and we see very similar sorts of convergence rates, but sort of the so this is here. This is, I called it Gauss-Newton, but it's also Levenberg-Marquardt with one of the parameters sent to zero. It's those are the same thing. Then you see very similar convergence rates and behaviors between those two algorithms. But then sort of Levenberg-Marquardt has a very obvious generalization to fitting multiple parameters, where Newton's method, this is sort of one way of doing it. There's possible other ways, but this one has a slower convergence when you generalize it to fitting multiple parameters. Yeah, and so here's just looking at the convergence of, so this is now fitting, so if we go back here, so this is fitting C1, C1, C2, and C3 here at once here. And we see that Levenberg-Marquardt has a very nice sort of straightforward generalization to fitting three parameters. And lastly, we consider sort of what happens when so here we can apply, on previous problems we can apply either root finding or optimization methods, because we have some exact values of the parameters, right? But now, suppose that this is sort of, we add this extra term, and this is standard for sort of some like small scale behavior that's not being modeled in the system. So it's use a higher order derivative here. And so epsilon is here small, but then we consider fitting our 3 parameters without modeling this 6th order term. And we see here, right, that Newton's method, this is Newton's root finding method, doesn't work well for this, and this is because it's a root finding method, right? So in particular, Newton's method looks like C sub I equals the error over the derivative in the error, right? So this is our new parameter update step, right? But if the error doesn't go to 0 and the derivative goes to 0, what happens is it will sort of approach 0, but then as it gets really far away, it'll sort of be pushed away, and then it'll sort of approach again. Sort of that's, I think, what we're seeing here. And then if we look at, so sort of, this is on log scale, so it doesn't make it as clear sort of what sort of level of convergence we're getting in the Leavenworth-Marquardt optimization algorithm. Here we see, here we see, right, so our Leavenworth-Marquardt is, it's reducing the error by like, maybe a factor of 3 or something like that, right? And so it appears to sort of, it is working, but one of the things here is we see our long-term error isn't really, the derivative isn't really time independent because it's sort of having all these sort of rapid oscillations. And so there may be a better way to formulate the problem that sort of doesn't assume that the long-term error is time independent. So sort of next step is we want to do the sort of rigorous justification. Maybe we look at what the sort of exact convergence rate is, and first we'll do that for the finite dimensional case. And then another next step would be understand the dependence on hyperparameters like our delta t and our nudging parameter mu, and when the convergence might fail. We also might find connections to other parameter estimation approaches, specifically, so PWM, I should have referenced that paper at some point, but it's that's a method developed by Podshev, Whitehead, and McQueary, which is sort of a different approach for doing this parameter estimation. We want to see if there's sort of a relationship between those. And then maybe other things is sort of understanding how we could extend the continuous data assimilation nudging approach, and understanding sort of when that doesn't converge. And then lastly, also we could apply this to some real world models. And like my original thesis project was meant to be applying this to something else, and then we had to figure this out. Okay, thank you.